Hi everyone. So we know that from 2035 in Europe, internal combustion engines are not going to be welcome anymore. And if you read the text law, you understand that this applies for any brand that manufacture more than 1,000 cars. So if things goes at plan for now, it means like brand like Ferrari or Lamborghini will not be able to sell anymore hypercar with internal combustion engine. So this means they would have to develop fully electric EV, hypercar. So we can ask ourselves, is that really fully possible in 2035? And where are we today? What are the hypercar existing on the market? And what are the challenges? For this, I think it's time to ask a nerd. And for this, we are welcoming today Adriano. Hello, Adriano.
Hello, everyone.
Can you present yourself, please?
Yes, so I'm a battery pack and high voltage engineer in Manifattura Automobili Torino. Manifattura Automobili Torino is a boutique car manufacturer that develops small series and unique pieces of cars. I've been with Manifattura Automobili Torino since June 2020. And I have been developing the Aspark Owl, which is a project developed for the Aspark company, which is a Japanese company who wants to develop an hypercar EV.
Okay, we are going to talk about that in a few minutes. A question I ask usually to our guests: how did you end up to be in electric vehicle? Is that from your studies or you move on? How you end up to be in this field?
Yeah, it started when I joined the university here in Turin because I was always focused a lot with Formula One, and there is this student competition called Formula SAE. And in Turin was the second year they went full electric. They switched from combustion cars to full electric ones. And I just got involved with that. And I enjoyed the challenges, and I kept on with that.
Okay. So we are here for about 40 minutes. We are going to present a little bit an overview of some existing hypercars, and what exists on the market today. And then you will present more key elements about the Owl, feature like on the batteries, the e-motor, the electric drive unit, the chassis. And I know you have some secret ingredient at the end, so let's keep this for the end. And meanwhile, Tom will gather some questions and ask you maybe for more details after the presentation. So, of course, today, I think when people think about electric hypercar, the first thing they have is Rimac. So I made an extensive review of what is available publicly on the development of the Rimac. The cars start to be delivered, if I'm correct, but it was relatively long. They came to the C2 and deliver the things. We also know that so one first things we can discuss together is the fact that hypercar usually do not get this flat skateboard usual platform. They have usually a chest for the battery. Do you have any comment about the Rimac? I guess you are very familiar with this platform, right?
Yeah, well, one of the challenge in building an hypercar is that you want to keep the H point, so the hip point, very low to the ground. So it is easier with a four-door saloon because maybe you can make it a little bit taller and just make the battery below your feet. While you have to work there with a very low H point, you cannot put anything under the seat. So everything that is left is the central tunnel and in the back. Also, because of weight balance, you don't want a huge mass just in the back, but you want to distribute it a bit. And it's definitely a challenge for an hypercar because also to have a good aerodynamic, you need a small frontal cross section, so you cannot go very high. And that's the the optimum at the moment. More or less everyone agreed on this topology, let's say.
Something surprising for me about the Nevera is the fact that they now came to this sort of double sandwich of cooling plate, because Rimac was very well known for their immersion cooling they've used for the Koenigsegg, for example, but I know it's a hybrid, so that's slightly different. Is that surprising for you? They came back to a cooling plate here, or?
Well, you got a lot of challenges in doing both, because it seems like with immersion cooling you can achieve a greater performance, but then you have to take into account that the cylindrical cells are preferential in axial conduction rather than radial conduction. I'm talking about the heat conduction. So I mean, when you add immersion cooling, you add also a lot of complexity, because you need to use a very special dielectric oil, which has its challenges with silicones and with the pumps, because some pumps cannot really move it or will get damaged with silicone, with this dielectric oil. So in the end, the cooling plate, it's a little bit easier on the cooling side. You have still other challenges, such as keeping the cooling plate insulated electrically from the cell, but it's just a question how much you want to, where you want to have your challenges.
Another very famous hypercar, which is for me the first true hypercar fully electric, is the NIO EP9. So you mentioned about cylindrical cell. We also can say that a lot of high performance and yes, very high performance application use pouch cells. So for example, the EP9 is pouch cell. And one specificity of this car is that it has a packaging each side of the car, so it can be removed from the side of the car, and it's swapping battery in this car. But I know that there have been, first, it's not road legal. This car is not road legal. It's very big difference. But at the same time, it was developed relatively a long time ago for a car. So it's not like an antique car, but for electric car, it's relatively old. We have also discussed in a previous episode of AskANerd with David White from Deneca the fact that if you want to target high performance, obviously you want to get very high power, which means high C rate. And you have a compromise to do between the range you can achieve and the power you can have. And if you want to get a compromise between both, finding a chemistry correct for this is difficult. I know from the review I have found you give me for the Owl that you have a pretty good range and a very high power. Do you have any advice for people how to get this challenge between finding the right chemistry, or?
Well, it's important to define the mission. The mission of the Aspark Owl is to get the range, but its main goal is to have the fastest accelerating EV on the market.
So you mean your priority is the high power rather than really the range?
Yeah.
Is high power, okay. But still you get a reasonable range, I think. We will see that later in the presentation. And as we have discussed also, there are some patents coming. So there is a recent patent I have also reviewed from Ferrari. Again, here we see this chest you have already discussed. But here they also get the possibility to get mixing of different cells format, mixing of different maybe cells chemistry. Do you think Hypercar gets the mission to be a sort of development lab for idea for future technologies for EV? I see them like that, but do you think it's one possibility to use them like that?
Yes, you can definitely go to the forefront of technology with this. I mean, it's the same concept that the Volkswagen Group applied when they bought Bugatti and they developed this crazy car with 4 turbos, direct injection, and four-wheel drive, and so on. If developing a project like this sets you free from a lot of other constraints, so you can go above what is the current capability of the technology.
So let's see what choice of technology you have made in the slide after this one. I just want to mention that for me, one other key point is that today we still do not have fully EV car racing at Le Mans, and maybe developing things like this hypercar will bring something that possibly races at Le Mans, even if today we hear a lot about hydrogen. Do you believe that hydrogen is a competition technology for hypercar today?
Well, the problem with hypercars in competition is that you need to be flat out a lot of the times, and it is definitely a challenge for battery electric vehicles. But I think it's even more a challenge for fuel cell electric vehicles because a Toyota Mirai has a fuel cell of 150 kilowatts peak, I guess, and you are flat out in the realm of 300 to 400 kilowatts for 60-70% of the lap on this kind of cars, and it's not really simple to get to have bigger fuel cells and so on. I guess that some possibilities in developing new fast charging methods, and maybe the complexity of the immersion cooling is definitely worthwhile in these applications. But personally, I'm not a huge fan of hydrogen. Maybe there is some possibility, but I don't know. We will see.
So now let's talk more. We all want to know more about the Owl. So what can you say about these cars, and what is the role of your company in the development of this car?
Yes, so I joined MIT when this project was well underway and was in its testing. So I have to say a lot of the terrific work done in this company was done by my colleagues, but the main let's say boundary conditions for this car was to have the fastest accelerating road legal EV, while maintaining a lot of critical comforts, while maintaining a very specific styles developed by Aspark, this Japanese company. You have actually air conditioning, infotainment, height adjustable suspension to not touch the car on road bumps.
A true luxury car, you mean?
Sorry?
A true luxury car, not specifically designed for track. It's designed for very rich people, but to be used legally, street legal, you mean?
No. It's actually it is not yet street legal because we are finishing the homologations, but it will be homologated as a. It's the homologation done just for small series production, but it is completely road legal, and it will have its plate. They already have their chassis number. We did a lot of testing. It's actually a competitor to the Rimac Nevera. I would say the philosophy it's a little bit different, but it is a completely road legal car.
You are able to make 0 to 60 miles per hour in 1.72 seconds, which is, by the way, less. It's better than faster than the Nevera Rimac, which is somewhere 1.9, if I'm correct. I don't remember, 1.83, something like that. At least it's better than the Nevera.
Yes.
I think first, for people listening to us, it's really crazy. You start, you are just stopped. You fake 1, 2 seconds after, you are 100 kilometers. Personally, I think it's crazy, but
a nice episode that happened during development is that not all the drivers that we tested were able to not lift off from the accelerator when they experienced the instant torque. And I have driven it on small stretches of yes, and even on the track I've tried it, and it's really mind-blowing. You get the sensation, okay, this is not normal. Maybe it's you feel like you're losing control. Sorry,
it's a two-seat. It's a two-seat car,
yes.
Right? You can be
You get also some luggage space, but no more than a weekend luggage space, I would say.
Nice weekend in Monaco or something like that. So, can you talk about what you have developed? And I know you are going to detail all of this, but this is an overview of the key technology. All of these bits have been developed by MAT.
Yes and no. I would say this car takes what is available now on the market to its limit. Some things like the chassis, the suspension, and the control system were developed in-house or with close ties to a supplier. Some things that require too much engineering effort to develop in-house, like the inverters and the motors, are actually bought from Cascadia Motion, which is a very good supplier of us. While for other components, there was a sort of co-design. They were coming to the market with this product. We did some part of development for them, like the validation. We validated it together and so on. But everything, we tried to keep it as much as not develop crazy things as possible. The battery is the last element that we began a development with a company. Then we decided to part ways, and we are now developing for completely internally.
So let's start with the battery. So you say it is 800 volt, which is now relatively common. That's surprising for sure. You mentioned NMC chemistry, and you can see that the peak power is 1.1 megawatts. I'm surprised also by the fact the size, the capacity of the battery is some kind of relatively small. I mean, I know it's not meaning anything in terms of whatever else than the capacity. But if I compare, for example, with the Rimac, which is, if I remember, 120 kilowatt hour, you are definitely a much smaller battery size.
Yes, as I mentioned before, the style was actually very, very, it was a hard point for the customer. They wanted the car styled exactly like that. This car is very low. It has just 90 centimeters of height. So this battery is definitely a big engineering job, but it's the result of a compromise. Also because the more cell you stuff in the battery, the more weight you add on. And from the reports that I saw online, the Aspark Owl is a little bit lighter than the Rimac Nevera. But in the end, they are still hypercars, but the philosophy it's a little bit different between the two. They went for what is the best technology, even developing a lot of parts specifically for it, like the inverter and the motor. We tried a more mainstream approach, work with the best that it is already available. So this is our compromise.
An Evera is about roughly 6,000 cells, cylindrical cells. I personally estimate that you must be around 4,000 here. Am I far from this value, or can you say something?
They have a different format.
Okay, interesting.
Yeah.
Also, something very crazy, if I can say also, is that you have a capacity of 69 kilowatt hour and a peak power of 1.1. This means a C rate of 15, if I'm correct, right?
Yes, you're correct. This peak power that we refer on is obviously limited to track use. We do not recommend our customers to use this amount of power on the road. We think that let's say 600 kilowatts is enough to play on the road. I'm personally even less, but this kind of peak power, you have a lot of calibration, and you also need to heat up a bit the battery because the cells behave in a way that their internal resistance is actually lower at higher temperatures. But then you need to be a little bit careful with the cooling system and so on. So this peak power is obtainable, definitely on every car, but you have to do it in very specific condition.
Anyway, if you are 100 kilometers per hour in 2 seconds, you cannot be because in front of my house, it's not possible. So now let's talk a little bit about the e-motor, the electric drive unit, and maybe some of the cooling. So what can you explain us here?
So as you can see, it's everything is very complex. You can see that the light blue stuff is the cooling system. The orange stuff is the high voltage traction pad, while the green stuff is just the mechanical transmission. We have 4 independent motors controlled by 4 independent inverters. So we can enable a full torque vectoring. Every wheel is independent. Every wheel can be stopped at any time. And we have 4 transmissions, which are coupled in the front and in the rear. In the rear, we have also, let's say, similarly to the Porsche Taycan, a gear shift, which shift both transmission at the same time with synchronizers. And this allows us to have with a motor already present on the market, we can reach both the 0 to 60 miles per hour in 1.72 seconds and 300 above kilometers per hour, which is not simple with a single reduction. You need a two gearbox to achieve both of these requirements if you don't want to go the Rimac way with the high spinning electric machine. As I was mentioning before, we have also this quite complex cooling system, which also integrates the air conditioning system. This air conditioning system is also able to chill the rear inverters and the battery, as the most power is for the rear inverters and also the battery is what heats up more when you're using in flat out.
The way you are saying this, it seems that it's really a challenge to keep cool down the inverter, because very often we talk about cooling the batteries. We do not hear that much about cooling of the inverter, but yeah, they are.
Yeah, the thing is you have a lot of thermal mass in the battery, which will eventually heat up, but it's kind of slow. While the inverters being more compact than the battery, they heat up faster, also because we are driving a lot of power through them. But in the end, we didn't have any issue, honestly, with this system. It's there because we had to switch it on sometimes, but it just works.
So now we move on to the chassis and the suspension. Is that something also MAT has been involved in?
Yes, definitely. The chassis is not produced in-house, but it was completely designed in-house.
Okay.
This is really a terrific job, as you can see that this bathtub just weighs 118 kilogram, which is really low for carbon fiber. This is produced by one of our key suppliers as well. Also, the suspension, maybe you cannot really see it from these images, but it's a front and rear pull rod scheme. You have completely adjustable Hollins dampers. You can, if you want on the track, you can play with everything, with the rigidity of the spring, with the actuation of the dampers. I would say it's really a playground if you want on the track. And also, sorry.
No, go on.
And also we have this continuously adjustable ride height. And since we had already this hydraulic system to control the ride height and also the rear gear shift, we also have an active rear wing which can act also as an aero brake.
That's cool.
And it's definitely helpful to cool down the charger when it's really hot, as there is a small vent below that, so we make the wing raise and to give more air to the electronics.
In the slide you have prepared, you mentioned aero brake mode. What do you mean here?
That the wing is fully developed and then it is tilted, so it actually increases drag, so you can brake faster.
You mean like a plane when you land and it's making this to help stopping? Yeah,
Yep.
Okay. You didn't mention anything here, but I guess also you have energy recovery at braking.
Yeah. Obviously, we have energy recovery, as it is free with a fully electric EV. Yeah.
Impressive. So here, I don't know, I guess you want to play maybe the video. So first, let's remind people that this video is 60 times slower, if I'm correct about what you say. So I will play the video first and we are coming back. I think it needs to load for just 1 or 2 seconds, but it should come.
Yeah, in this video, you can see that the importance of the software and of the control system as...
So it's slow down first for people to understand. It's really slow down because all of this happened.
Yeah. You can see that now maybe it's not so visible, but there is the rear. Yeah, now the rear wheel is leaping, and the control system is catching up on that through the wheel speed sensor, and it is just cutting the torque to that wheel, so that the traction control system can then recover. It's yeah, I'm sorry, it is not so clear with this stream, but it works really, really well when you see it in person.
I like in person when you see that happening, like in, I don't know what, because it's you say 6 times slower.
Yeah, no, sorry. I mean, yeah, just the quality of the stream. Maybe it's not enough, but you can actually see from some other video that the wheel is spinning and the traction control system is locking it in, or it is reducing the torque, so it catches up with the other. You can see actually the difference of the two wheels and the wheels that goes like this.
Okay. Do you want to add anything about the electronic or some of the power electronic, maybe some control?
Yeah, for us, the big step in MAT's development was really developing the full software of this car, so that you can control pretty much everything. You can. It's a lot of calibration work and a lot of parameters to set up, but we are really in control of everything that the car can do. For example, we tried, just as a gimmick, to simulate gear changes on our car. So you can just touch some buttons on the steering wheel and the car acts like it's downshifting or upshifting like a ICE vehicle. And this is enabled only if you control all the software of the car.
So one of the last slides is about the tires you have used, and you mentioned, I thought it was intriguing when I read your slide the first time, as a technology, the tarmac, and that's something interesting. Can you say a few things about that? So you are using specific tire, if I correctly understand, but also the asphalt of the track when you run the car is very good quality for making this record, right?
Yes. So if you look at the physics of what makes a car accelerate a lot, actually a lot of stuff cancels out. And what is really critical, as long as you have the power to put down on the street, is achieving the best possible friction coefficient between the tire and the tarmac. So you can control a lot of stuff, and we actually did a design of experiment on various parameters, both for the traction control and for the parameters of the tires. But what we ended up is that a good tarmac is able to extract more than a very bad tarmac. And we really went in more than one circuit to try the best tarmac and changing this and that parameter. But what we ended up is that a circuit like Misano is the best to have this kind of performance.
One question I have is that when you make this acceleration, so 0, 100 kilometers per hour to second, can the tire make this several times, or each time you are trying to make this record, each time you are doing this?
No, actually, because these tires works best when they're in temperature, you actually need to do it a lot of times. Okay. And if you take the tires at the right temperature, actually your times could improve a bit.
Okay.
improve but decrease. Yeah.
Now we are coming to the super secret ingredients, all the secret of the Owl. What can you say about that? What is a secret ingredient for you?
Yeah, it's a lot of work, a lot of teamwork, as there were tireless nights, a lot of days on the tracks. With we actually did this test in Misano with 40 degrees. I think that the asphalt was actually at 45 to 48 degrees. It was very hot, and you're practically in the sea there. And we did this test year round. You can see there is another photo of a test, I think in November or February. No, I think this is, yeah, this is already maybe April.
I guess people working on this project, everyone in the team and so on, all these people are passionate people by, yes, good engineering and passionate about that. This is the way we imagine people working on hypercar.
Yeah, and what I should add, you also need to have a little bit of craziness and vision that, as our CEO has, that even if it is not possible now, you still have to try it. And if you keep trying, maybe you won't achieve it 100%, but 95 is still very good. And I think with this project, what Matt achieved is 105% of what was the initial goal.
You can very well see on these pictures that the Owl is really small, like 1 meter. You mentioned less than 1 meter, and you can see compared to people that the car is super low.
Yeah, it's not a car for people who have back problems at all, because it's not so comfortable to get in and out.
So this is the end of this discussion. Now I give everything to Tom, and he's going to ask you some other question. I guess he has tons of them.
Lost control of my mic for a minute there. Hats off to you, first of all. Hats off to Matt for what an achievement. That's a fantastic time, isn't it? It's great to see another Formula student graduate doing some exciting stuff in the industry as well. I was running some numbers while you were chatting, and I guess the first question is, where do you think the limit is now in terms of like the achievement of the time, and where could you go next? So I ran the numbers on the motors, and it looks like you've got like 1.5 megawatts of motor capability versus 1.1 in the battery. But then there's also the traction limit. It looks like the inverter current is 2 megawatts and kind of out of the way for now. Where do you think the limit is, and where could you make the next incremental step?
Well, on the 0 to 60 mile per hours, there is still a little bit of improvement possible, but in the end, the problem is finding the tarmac at the right condition, and maybe having a better gripping tire. So that's not what we aim currently. We are looking to set some other records. So not the 0 to 60, but there is other speeds.
There's loads to go after, isn't there? Yeah.
Yeah.
My background was doing repeatable 0 to 60s in combustion engine cars, where you tend to get the performance tends to fall off as the thermal mass of the engine climbs. Then you have to derate the power available in general. You've obviously already got 4-wheel drive as well. You mentioned the transmission system as well. Is that a unique MAT piece of work as well, is it? Or is that an off-the-shelf part of the...
It's a co-design with one of our supplier, actually a French supplier.
Okay. The other question was going to be, I mean, we talked about where your physical limits are. How much of the time, and this is going back to experience of combustion engines, how much of that time is made up with the control system? And is there anything you've done in terms of positioning modules or organizing the compute, if you like, centralized compute, to mitigate the response time as well from driver tip-in into torque at the wheels?
So from driver input to torque at the wheels, not really. The one interesting thing is that on the 0 to 100, 2 to 3 tenths of a seconds are lost just for the first wheel movement. So that was really critical to get a good traction from the start. And we played a lot with the parameters for the traction control and with the pressure and temperature of the tires. But what definitely helped was that the wheel speed sensor are directly put through the vehicle control unit. And it also has an inertial system which measures the acceleration also on its own, so it can compare, and it knows instantly when the car is when one wheel is drifting away from the correct traction path.
Yeah, because architecturally, that's typically where you'd lose a chunk of time going through the ABS unit and into the powertrain controller.
Actually, it goes through the ABS unit, but the ABS unit relays it back as not as a digital signal, but as an analog signal.
Right.
So everything goes there and then comes back, but it's at the speed of light, so you don't really care.
Yeah, it's fractions. Yeah. So I guess the final question: what's next for Aptera? You've mentioned some different challenges in terms of records. Is there anything else that you're looking at in terms of vehicles, or is the vehicles going to evolve over time to meet those new record targets?
There are a bit of record targets that we want to try. As I mentioned earlier, we are currently in the stage of redeveloping a new battery for this vehicle. And this is our main effort at the moment, so we can also conclude the homologation and get this vehicle on the market and pursue those other records. There may be something else coming, but I'm not allowed to talk about.
One of those. Understandable. Okay, I think at this point we'll bring back Cecile and say thanks very much for your time. That was a really interesting deep dive into the Aptera. I think for our audience, if you found that exciting, don't forget to subscribe to the channel and hit the notifications bell for future episodes.
Have you booked for yourself one of these cars, Adriano, or you are not going to buy it?
And I've booked, sorry?
Are you going to buy one of these cars? It's a joke.
I hope. No, it's there is the price. The price is public on some publications, but it's very, very high.
Yeah, it's cars we are talking about million.
I mean, you can still, if you are developing it, you still need to try it out from time to time. But
that's nice. That's the nice part of the job. I mean, I guess when you are working night and nights, it's more difficult. But when you are driving the car, it must be rewarding.
The engineer's advantage.
Yeah.
So congratulations. And we hope to get you another time for another episode, maybe on another car if you have another announcement to say.
Yeah. Well, in MIT, we are always open to develop new stuff. We will get you a call if everything else comes out.
So thank you very much. And bye-bye for now.
Thank you guys. See you later.
Bye.